On a Maxwell-Boltzmann distribution of reactant particle velocities, all particles above a certain threshold of energy have enough energy to potentially initiate a reaction. A Maxwell-Boltzmann distribution looks like what we see here. You might have seen this if you studied gas laws in earlier studies of chemistry. What we're showing on this distribution is, on the horizontal axis, we're showing the speed of the particles, with slow being on the left and fast on the right. And on the vertical axis, we're showing how many particles. You can see with this distribution that we see here, we have a comparatively small number of particles that are traveling very, very slowly. As the speed increases, there are more particles that are going this speed. You can tell that the most particles are traveling at this speed right there that I'm touching with my laser pointer. And there are a very small number that are going comparatively fast. I'm going to call this the cold reactance curve. We're going to distinguish it from the warm reactance curve in a minute. For a given reaction, the particles have to have a certain amount of energy in order to even have the possibility of reacting. So I'm just going to arbitrarily pick a speed, and I'm going to say this speed right here, this is the speed that a particle in this reaction has to have if it has the possibility of reacting. Vertically from that speed, I'm going to draw what I call the activation energy line. What that means is, below that line, the particles have no chance of reacting. If a particle is above that line, then it potentially could react if it hits the other reactant particle with the right orientation. We talked in a previous lesson how it's not just enough to have the right amount of energy. You also have to collide with the right particle orientation. The particles to the right of this line could potentially react. The ones on the left have absolutely no chance of reacting. If we were to try to figure out what percentage potentially could react, we would have to find the area of this green hatched section compared to the area of the whole curve. And that proportion would give us the fraction that might have a chance of reacting. Look what happens when we warm this reactant system up. When we warm this reactant system up, the distribution broadens and the particles on average move faster. Because it's the same reaction, the activation energy line hasn't moved. And you can see what happens. When we warm up the reactants, a much larger fraction of them, that is this green hatched area compared to the overall area underneath this whole curve, there are a much higher percentage of particles that potentially could react when the reactants are warmer. As the temperature increases, the Maxwell-Boltzmann distribution broadens. It also shifts to the right, but it broadens. The activation energy line remains in place, so the percentage of particles that have enough energy to potentially react has increased. Let's summarize what we've talked about. A Maxwell-Boltzmann distribution shows the relative number of particles that have certain speeds in a sample of reactants. The higher the temperature, the broader, and not as tall, the distribution. And on average, those particles are going faster. The speed above which the particles have enough energy to possibly react is fixed for a given reaction. In other words, the activation energy is fixed. And the proportion of particles having this speed is found by finding the area under the curve beyond what we might call the activation energy line.